coming to me. I just need this to be real. I don't need no fairy tale. You don't need a kill, pregnant for me. Ooh, I don't need no fairy tale. Run and go still every time. Whatever it is, I keep on trying. 'Cause it ain't hard to forgive when you know what it's like. That's why I'm better with than without you. Oh, I'm on it, I want it, but why do you seem to call it your eyes? I can't tell if you're here or you're out there. Do you wanna be out there? You don't need to be Prince Charming to me. I just need this to be real. I don't need no fairy tale. You don't need a kill, pregnant for me. Ooh, I don't need no fairy tale. You don't need to be Prince Charming to me. I just need this to be real. I don't need no fairy tale. You don't need a kill, pregnant for me. Ooh, I don't need no fairy tale. I don't need no.
How many lives does it take to realize what's going on? How many years have gone by? When will I reach the finish line? Does it ever end? Is there some reason to all of this? Bit by bit, to all of this. Bit by bit, to all of this. Bit by bit, to all of this. Bit by bit, to all of this.
Hello again, back at it with some more work on the nightmare courses, more binary exploitation, and we'll just jump into it. I'm gonna load up some music on my, you won't hear it on the stream, but I'll have something to listen to while I go through this. Alright, so the next challenge that we're going to tackle is from the Seesaw Qualifiers 2018 called Get It. I've already copied the binary. Let's go ahead and check it out with file. It's a 64-bit executable, dynamically linked, not stripped, that's helpful. And we can go ahead and see what protections are on it. We've got alright, so we have partial rel row, no stack canaries, stack is not executable. I think that's NX. I mean, that like NX is for no execute bit kind of thing, but I don't know if that is specifically for the stack. I should probably figure these things out at some point. And then it's not PIE, so shouldn't have any sort of ASLR protection possibility with it. Let's go ahead and run it. No, I don't get it. Okay. Well, this one they literally say gets, right? Instead, so I'm going to go ahead and assume that they're calling gets at some point. Can we... Do I want to look at this in radar? Do I want to just throw it in GDB? And let's do another one of these. We'll get the De Bruyn, however it's pronounced, sequence. And I'll just throw it in GDB so that we can see we got the seg fault, so that's good. So we start at AAO. So this all is the sort of prefix garbage. And we got 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 35, and 38. Let's give that a shot. I guess I will maybe want to look at it in radar to figure out what function we're trying to return to. If I throw this in, oops. Yeah, we still get address null. I don't know if I'm just misunderstanding how to use strace. I would have thought that I would get, like, it tried to jump to whatever address is referred to, you know, is this. But setting that aside, let's just pop it in R2 and see what other functions we've got. We have main, give shell, that's probably the one we want to look at. And that runs bin bash system. Okay. Create our flag file. Should have stayed in. So give shell is at this address. I think it's going to be a fixed address just based on the way this works. And this one does not leak a pointer to anything. So what am I saying? So I'm gonna have to assume that there, you know, my reading about the PIE stuff, meaning there's no ASLR enabled on this, or it's not that ASLR gets enabled on the binary, but it wouldn't be possible for the ASLR system in the kernel loading of the binary to work because it's not position independent, and if it was loaded at using ASLR, then we would have no leak to know where to put what kind of address to use for the return point override. So I'm going to just assume a fixed address. So we've got that as our address, and then the payload is going to be What did I say it was? 38. So 16 hex. And then address for that give shell adder function. We might have to do the same thing that we did with the previous seesaw. This one was done in 2018, so maybe they created it in such a way that it doesn't trigger that issue with the move APS instruction. But if it happens to, if we still don't get the shell and all of that, then I will look for that right away, and it should be a pretty simple fix, ideally, if there's a push at the beginning of that function. I didn't look at it closely enough to see whether it had one or not. We'll find out. Right, target dot. I think we'll just receive one line. Then we'll send the payload line. And I guess we'll do interactive after that because it gives us a shell. That should allow us to print out the flag. Oh, I forgot to encode that. I thought about it when I was writing it and then forgot. Nope. We got the EOF, so it must have crashed, I guess. It just stopped with an exit code. Alright, so I was not triggering the overflow. Sorry, this needs to be 26, not 16. Now it had a seg fault. Okay. Right, and if I do, I'm not actually in the shell. Okay. Let's think about this. Where are we getting the... Well, let's print out the payload and see what happens. When we run this in GDB. All right. So where did RIP go? 4005. Okay, I am on the wrong. My offset is incorrect, I guess. Maybe I counted incorrectly. I should have just done what I did the last time. So we are at AAO AAP. Let me just see the length of that. I guess I could even throw it in. $40. Okay, yeah, I'm just bad at counting. I should not rely on counting by hand. And still got the seg fault. Okay, interesting. just manually delete all that. Try it in GDB. Okay. And now pointer is what I would think is a valid pointer for, pretty sure that's what I had from Vim. Or what do we call it? Give shell in this one. 405b6. Oh, I'm still off. I'm now too short. We're reading an extra byte in the address. Maybe I copied that wrong out of Radar? No, so then where is the C2 coming from? That must have been already on the stack somewhere in our... Okay, so we want one more? Nope. So if we have 405b6 C2, that means we want one less, I think, because this is going to be at the lowest address, and we want this at the lowest address, so we've pushed one bit too far. I still don't understand why this would be a C2 and not like 41. I'm probably still messing this up. But let's... just copy it now. What the fuck? What did I do there? Nonsense. And now I have that ridiculous file name. Great. Okay, so now we do get the, okay, so it was 1 minus was what we needed, because, yeah, we were just a bit too short. I don't... Of course, the process of working with this in GDB, when in theory it's a remote binary, is, it's questionable. I should try to figure out if I can do one of these without using GDB at all, because that might be more realistic of a scenario for exploiting a binary that you don't... I mean, certainly if you don't have access to the binary, attaching to it with GDB is not going to work. So, but I just don't know if that's really the scenario where people are developing these sorts of exploits, or if there's an assumption that you develop the exploit when you have access to the binary. Certainly you could fuzz the remote binary and then sort out, the length of the buffer overflow is. It just seems like you'd be in the blind, like in the dark so much. Anyways, so now we're at a scenario where the stack is misaligned. So let's look at, can we just jump one further? Seems like we can do that. And still doesn't like it. Interesting. This definitely seems like it is going to work in GDB. Yeah. So what the hell? Why is it just seg faulting? Can we rather than work with it interactively, just run that command? Looks like no. And this is, again, not a scenario where I need to know the exact stack addresses. I mean, maybe it's an ASLR thing. Turn off ASLR. Still didn't get it. Okay. Where am I going wrong with that? So I have the right stuff in exploit.txt, so where are we getting the seg fault in the child? We don't even have I don't see anything, but we're getting the seg fault at this address. Let's see if that's the same address every time. Okay, yeah. I mean, I did turn off ASLR, so it should be. Okay. But if I and it runs through it here, so all right, so I guess what I want to do really is set the breakpoint at this address and then just rerun it and rather than a catch. I don't want to do the catch thing. Maybe it's not segfaulting in the child, but okay. Do I... Is it something to do with like I mean gets is gonna just read until it gets a new line, so I have to send the new line. So I'm wondering if it's like starting the child and then the segfault is in the parent, but it didn't do anything. Oh no, it's just I'm not seeing it because I'm not doing -f. Right, let's do the strace again. Okay. Not seeing a segfault in the child at all. So why is it? Well, I guess partly that is because I need to let me go ahead and throw the command on there. So first off, running sh, does it ever read? Oh, okay. Of course, it's gonna have some. No, so it's not reading. It is definitely. I mean, this is like. Don't. Right? We do whatever that is, and then, you know, we do the exploit, the payload, we cat something. But why is the shell not getting anything from standard in? It's trying to do a read right there. And its file descriptor 0 should be copied over, I would think. I don't know. What am I misunderstanding here? I really thought I was gonna like get one of these at a reasonable, like finish it and then move on to the next one like it was nothing. But every time I come up against, I don't understand some shit, and I just can't get it to work. And so often it feels like it's not the core of the thing that I'm supposed to understand in order to get through the challenge, but it is ultimately not something that, it still prevents me from being successful, but it's some separate element, not the main idea in the challenge, which is overwrite the return pointer to go to that function. So, what the hell? What the hell? Let me see what gets does in case I am misunderstanding. So terminating new line or EOF. Yeah. I mean, I could put more new lines in here, but the one should be enough. Maybe it reads multiple times, but there was nothing in strace to indicate that it read. Why don't I can tell it to if I tell it to show me the full string for the reads that it does. So it got 62, which to me indicates that it actually did read beyond. Maybe I need to fill up that buffer because it's been buffered in the parent. So it read 62 bytes. I know that I've got 40 bytes, 39 bytes of sort of prefix whatever, and then 8 bytes of the address, and then a new line. So that's just 48 bytes. So where are the other 14 bytes coming from? The only thing I can think of is that it is this, maybe? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, I guess. Yeah. So if I why don't we just cat flag that txt again? Right, and then we do read. No, is that not what I'm supposed to do? Maybe it's capital E. I should just be able to say, alright, well, I'll say E trace equals read, I guess. Nothing, great. Oh, because I'm grepping on it. Yeah, fine. Oops, deleted the wrong thing. Okay, so now it is getting 75. So like, do I need to actually send it 4096 to fill up that buffer so that it has something to read afterwards? Let's give it a shot. So we're subtracting an additional 1 for the new line. So this should give us a buffer that's exactly 4096. I think once we okay, and then I'm going to subtract 2 because I am going to send it with a new line when I call send line payload. Just do it this way. I could do this, and so print out the payload. Because I still kind of want to, I need to throw that in a file. Should I open a file and write it? How do I do that? With you're gonna, is that really the best page to give me for the with keyword? All right, let's just look at. Okay, so we open and then okay. Wow. I hate the encoding issues in Python 3. Just open it as binary. Okay. Right. So we have, and then we have the address, which is going to be, yeah, okay. So let's look at what happens when we do it this way. It only reads 4094. So I guess I don't need to subtract 2. Let's think about this. And then I guess just subtract 1. What a fun language. Does that work? Okay. Alright, so now we are writing exactly 4096. Still doesn't read anything more, so it's not really a buffering issue, which, I mean, makes sense because it feels like get should only process some of whatever the buffer is. Why? Oh, well, at this point, it's the address is off. How is the address off at this point? Yeah, okay. Somehow that was enough. Okay. Pretty wild to me. And then if I echo that, run strace again, now it reads the flag. Well, just always some little thing that I don't understand why we needed to fill the read buffer. Not the buffer that like on the stack, because that overflowed it after 40 bytes. But we needed to send 4096 bytes so that the next read by the inferior process or the child processor, however it's referred to, read something else. Like, there's really nothing to this. Maybe that's why some of the earlier challenges don't or call set vbuff so that we set a 0 length buffer or a very short buffer, because otherwise you run into issues like this. Maybe I'll be curious to see. Just exit out, man. Yeah, I will be curious to see whether it comes up in the explanation. Alright, so let's read through their walkthrough. They run file on it, they run checksec, then they run the program, put in whatever their standard input number is. Yeah, an extremely simple function for main. There's no size restriction on gets, so it'll just scan until it gets the new line character EOF. Sure. I mean, one of the things that this is like every write-up is just re-explaining how the exploit works, even though at this point this is, I guess this is technically only the second of the return pointer overwrites works. So, okay. Or challenges, not works, but like I don't really need an explanation of that. I mean, obviously I don't need it from my experience, but also do they not explain that exact same thing right here? They actually explain it not as well, not as thoroughly in the write-up for the challenge that comes first in their list, which is interesting. Now they decide, okay, well, let's give you the full explanation of what's happening when you call into a function. All right. And then, yeah, 8 bytes for the base pointer that was pushed. Double check. Nobody is watching the stream. Oh, there's one viewer, I guess. Hello, if there's somebody watching the stream at the moment. My guess is we're not going to see, I don't see anything to indicate that they needed to do the additional post overflow padding to fill out the read buffer. So just something different on the VM system that I have set up, which is, you know, that's the nature of these kinds of things, is they're so particular to the exact setup of the system that you are trying to exploit. But it becomes pretty frustrating, especially in this scenario where somebody has created a challenge with an explicit here's how you should exploit it kind of structure like you would have for a CTF challenge, and then oh, there's some other detail in the way that prevents you from actually doing the exploit. Regardless, I figured out the solution to my extraneous problem a lot faster than I did on the previous stream, so I guess I should consider that a win. Alright, now we have the last of the calling a function ones before we start having to write in shellcode and jump to it on the stack. So let's see if this one goes any better. TU17 phone chat. All right. Oh, no. Okay, so we'll set up our flag.txt and just look at the program. 32-bit ELF binary. Okay. No rel-row, no stack canaries, no PIE. NX is enabled. All right. Let's run it. Okay. Let's try our De Bruijn sequence. See if that last bit is where the overflow is. Overflow might be on this one instead. wasn't far enough. We want to just go crazy with it. Alright, that might not be where the overflow is. Let's try it on the first one. Okay. So, yeah, we're overflowing something from the username. After how many bytes? $30 bytes. Okay. And then it treats that as the input. I mean, maybe like it reads 30 bytes and then I don't know. I think I want to look at this one in radar to better understand what it's doing. Alright, so we scan F. I guess that's not a string. Yeah, I thought we would be pushing the format string that's at that address, and then this would be where we write in yeah. Seems like this is going to be like, let me double check scanf. Alright. Format string, and then parameters. So this will be the format string, which we've just pushed that address. Oh, this is the actual string content? So 73, 30, 0, 33, 3, 25 is, oh, it's, what is this going to be, percent 30s, probably. So, yeah, we read in 30 bytes into buffer that is at 0x19. So is that I'm thinking that's 25 bytes. So then we've got an additional 5 bytes. Because the segfault was after this, so maybe the segfault was happening on the return. I mean, that would make the most sense. We are only reading 30 bytes in, so we need to put it at the last 4 bytes. Like, it doesn't seem like we would have enough space. We can run it in GDB and see what we actually overwrite to. the shorter one? Just do 40. I don't think it's going to matter because, again, I think it's only going to read in 30 bytes for the name. It will read in the other text, but oh, well, let's look at the other text just in case, but it didn't seem like I could overflow that. And in this case, we scan in another 30 bytes because I don't think we. Oh, this is. Right. Okay. This is a little bit of a cheat in the sense that I was watching somebody else go through this on the stream, and I believe the solution here was to overflow not the return pointer with the initial read coming from scanf. We don't have enough length to scan all, like, to read in to this buffer at EBP minus 19 hex. We don't have enough to cause it to overflow down through the pushed EBP and the return pointer. But we do have enough to cause it to overflow this, which is a short, just 4 bytes. I mean, it's a little bit wild that they're going like that the compiler would do it this way, but I guess it's understandable. So they have the string on the stack just pushed as a 4 byte value because the format string is only 4 bytes in this case. It's %30s, and when we scanf again, we load what we push as for the first parameter is a pointer to that stack location, and since we can actually overflow that from the first read, we overflow it with some other format string. In this case, we're probably going to do like %99s or something, like give it a much larger buffer that it will read from. And so this is now, it's reading into 2DH, but if we give it a large enough read, then as long as it's more than, what is that? 32 plus 13, so 45, then plus 4 for EBP is 49, and then, yeah, so if we read in 49 bytes, then the next 4 bytes will be overriding the return pointer, and so should be able to jump us to wherever we need to go. In this case, print flag, which is at that address. So we overflow by writing, I'm going to copy the address first, and then we overflow by writing 20 bytes, because 19 minus 5 is 15, or sorry, 14, which should be 20 bytes, and then after that we'll write our 4 bytes of format string, which can be any value above 53, I think, 53 or higher. So I will put in 53, I guess. I don't need it to be longer than that. And then the last 4 bytes of that will be where we put in the address of the function. What does that function look like? Call system again. So really we need to skip past this push. So we'll give it another can you how do I hate radar sometimes, most of the time, because I just don't know how to use it, but I just want to see, just put in these instruction addresses. Jesus Christ. Yeah, I'm gonna guess that it's 1 byte further than the address. So and okay, so we'll go 1 past that to skip the push. First thing we need to do is it's going to be a times 20 let's do it this way. Percent 53s and in this case we need 49 bytes. No, I'm going to put the +1 there. Space in. Oops. Okay, then we just need to receive until something. Then the first overflow. Then the other thing. And then receive everything. All right, let's run through the program again because I don't remember what the prompts are. So we need colon space and then another colon space. Okay. Wow. Let's see if that works. Nope, of course not. Of course I am doing something wrong. Well, let's print out our overflow. Gonna call them payload for consistency with all the other ones. see what happens with this one as well. What is going on? Oh, I was in edit mode. Alright, so I want to look at what the state of the what am I saying? Oh, we got somebody asking something in chat. I'm working on the nightmare challenges. I'll put the link in chat in a second. You can find it at this page on GitHub. So basically this is a course, roughly a course. It's just a collection of like a ton of different CTF challenges that are all pwnables of different sorts, and they've been organized into categories based on the kind of challenge. So I'm in various buffer overflow challenges right now. These earlier ones were just overflow a variable on the stack. Some of them might be like have an if statement to check that variable and see if it has a value that isn't what it was set to originally. So just an overflow that doesn't require you to think about like return pointers or anything. Right now I'm in overflows that are where you set the return pointer to some other function that's been written into the executable. So like this one has another function that just prints out the flag, and we are overflowing the return pointer on main to get it to return into that function because it doesn't get called anywhere, so there's no other way to trigger it. And then I think starting down here, just based on the names of the directories that these are in, this is where we're gonna put in shellcode and overflow the return pointer to jump to our shellcode on the stack. Some of these have like advanced versions with certain mitigations turned on. And so I'd definitely be curious how this one works with ASLR turned on, because I didn't see anything that leaked an address. Yeah, I guess. I mean, I feel like I could leak like a stack address by doing %p instead of %s when we are overwriting the format string, and then it would, well, that would, but it's a scanf, it's not a printf, so I don't know. I might look at this one next, but I'm not sure that I have a clue how I would go about handling those mitigations. And then later on, we get into some other kinds of buffer overflows that are primarily about dealing with certain mitigations, I guess. This one is called buffer overflow dynamic, like this section down here, so I don't even know what that would be referring to. Definitely curious. Then we've got format string based vulnerabilities. Somebody doing, what is it, like %i, I think, or no, %n. Yeah, that one's gonna be fun. Array index problems, not checking the boundaries on those. Bad seed, I guess, is like random seed related stuff. Getting into using static symbolic execution and like, I forget the right term, but I've used Z3 for one problem that I don't think is on this one. It was in Google's CTF last year in there. Like they had a real one in the real CTF, but they had a much simpler one in the did I use Z3 for that? I don't remember. I've used Z3 in one CTF challenge before, and that was kind of neat, so I'm happy to get more experience with it. And then a whole bunch of ROP stuff, heap exploits. Actually, there's more heap exploits than ROP stuff. Interesting. Overflow stuff. and I guess random other things. There's not like a lot of course content other than the fact that they all have write-ups. I don't know if this person did the write-ups for all of these. But you know, there's not a lot of like instructional material. It's really just here's, you know, several dozen CTF challenges in the ponables category, and here's write-ups for all of them, which is a nice sort of organizational thing to have, a nice collection to work through. And yeah, I'm just trying to have fun doing some practice because I don't do a lot of potable stuff. I've done more maybe on reversing. Even there, I'm not particularly experienced. And yeah, I mean, the fact that I haven't done a lot with it kind of flows out of the fact that every single time I try to do this, I think, okay, I figured it out pretty straightforward, and then I run into some issue that I am puzzling over for a while. That doesn't even necessarily seem related to the actual exploit, but it's just some other, you know, something gets in the way. So my experience level is still pretty low if I'm getting tripped up on all of these, and these are like entry level kind of challenges in most of these CTFs. Like this one was called warm up, this one is called shell easy. Like these are, you know, not the hard end of the ponables challenges in these particular CTFs. So okay, what was I going for? Oh, I wanted to set a breakpoint after we did the scanf so that I can see what has been overwritten on the stack. Okay, so at this point we have ESP points there. Where's RBP or EBP, I guess? No, is EBP minus 5? I think. I don't have. Yeah, that's okay. I'm not going to bother with that. Oh, but I can see it here, right? Yeah, EBP minus 5. So 18 minus 5, 13. Where is ESP? Is pointing at 13. So we have overwritten the format string that will be used on the next scanf call to be %53s. So then I want to set a breakpoint after the second scanf call and see what we get from that. Okay, so now have this as the address on the stack. Is that the right address for? I don't think that is the right address that we want to jump to. Yeah. Interesting. Where did I get that from? Okay. At least in one scenario we've got the B in there. So should I put an end line in here so that the printf doesn't mess up? It probably doesn't matter. I'm in puts. Does that work? Okay. Do that. That's what I should do, just NI. Okay. So yeah, I've got the wrong length for the second payload to overflow. So what happens when we get to the return? Oh, you know what? This looks like it's pointing to the right location. Right? We probably don't need to skip the push because this is 32-bit, and the issue that we were seeing with the system call is actually only on 64-bit, so I could skip that. But I'm not going to worry about that. I'm 26. Interesting. Did I am off by. Okay, whatever the fucking address I have here is just incorrect. I don't know if that's because I have it incorrectly in the exploit script or if I have done my overflow incorrectly. Let's look at it again. So 0485 C20 C2 6C. So 0485C. Okay. So we have that bit. So I am off. Why would I be off by 1.5 bytes? What is that about? Oh, well, okay. It's not 5C, it's 56C. So this is potentially just completely unrelated to the address that I thought I was putting in there. So maybe I am. All right. So let's get rid of the +1 in the first place. We don't actually need that. Let's just skip the push. So where are we going wrong here? I'm gonna do the thing that I actually did for the So we'll just save the exploit.txt and then have to do all that shit on the terminal. So I guess we should be seeing 6B 850408. Right? That's why we've got the L first. All right, so EIP 0. I guess I need to put the breakpoint on the return. Run it again. Okay. Now we have the right address. So now we're in print flag. Okay. So I did print that out. What did I do differently? I didn't think that I just took out the +1. Maybe that was enough. Maybe. Okay. Let me just try it without GDB then. Well, we did, right? And we didn't. We still get this. Yeah. Okay, now then, why are we? Not exploit.py. Alright, where are we getting the sig fault? In the parent. So this is writing. When we do strace, then what the hell am I saying? Send line. So if you happen to have any ideas, I'm all ears. But we are like, if I run it and pipe in exploit.txt, then it works. Good, we get the flag. So what I have for the exploit payloads is valid, but when I run it, oh, that might be all that we need. Forget that sometimes. Yeah, okay. Cool. So that one was pretty good. I messed myself up, I guess, with. I wonder if the +1 was actually an issue or not, and whether it was just me not printing the whole time. Yeah, so the +1 didn't actually matter. I just needed to have printed out the content that we got. That's fun. Okay. So this one was good, but it probably would have taken me a fair bit longer if I hadn't seen the stream where somebody went through the walkthrough and then I remembered that it was about overflowing to write the format string variable, which is then used in the second scanf. You can review the walkthrough real quick. They do file, they don't do checksec, but either way, 32-bit elf binary, run it, it prompts us for two separate inputs. The first is uname and the second is a string that is supposed to make it trust us. If we open it up in Ghidra, we can see it has this rough C code basically. So we've got 20-byte buffer for the name and a 20-byte buffer for the password. Interesting. Yeah, I guess it was 20 bytes. But then we probably, if you looked at the original C code, well, no, this is just going to say 30, right? It's not a hex versus decimal issue. It's just they've literally written a format string that is too long or that scans too much for the buffer they're using. We can see the stack layout in Ghidra has the password here. Why? Their stack layout is a little bit different than what I was seeing. But essentially we overflow this one into format, and then we overflow this one all the way back up to the return. Okay. So they're doing the math to figure out where they need to overflow. 10-byte overflow in both cases. They're given setup, we won't be able to get code execution with either overflow alone. However, with the first overflow, the one to name, we will be able to overwrite the value of format. This will allow us to specify how much data the second scanf call will scan. With that, we'll be able to scan in more than enough data to overwrite the saved return address and get code execution when the ret instruction executes. Sure. For what function to call? The printf function, print flag function rather. Yeah, it just calls system to print out the flag. Good. Ooh. And they open it up in GDB and do some stuff. And yeah, the alignment was kind of weird, but so be it. I guess there's no alignment requirements on 32-bit ABI. So what do? They do 99s, that's fine. And then they do 49 bytes, write the 4-byte address, same thing. Okay, cool. On to, let's see. So just clicking next, we get into the ASLR PIE. I wonder if this is, okay, I don't think there's actually a challenge associated with this one. Maybe this is just instructional material. This is the first time that I've seen any page on this that was beyond like the intro, about a very basic intro to assembly. Hadn't seen any information where it's just teaching, so let's read through this. With exploiting binaries, there are various mitigations that you will face that will make it harder to exploit. Defeating them is usually just one step for actually gaining control over a program, assuming that the mitigation stands in your way. Since it is just something that stands in your way, and since for the modules I like to cover a new type of bug or exploitation technique, I didn't make a module dedicated to each of the mitigations you will see. However, you still do see them, or some combination of them, nearly everywhere through this project. So the purpose of these is to give you a brief explanation as to what they are. So I think like down here, this one will be an explanation of the NX bit or other ways of turning off stack execution, I guess. This will explain what stack canaries are, what rel-row is about. Okay, that's cool. I think when we get down to here, it's just better organization of different kinds of ROP attacks, I guess. Yeah. So, let's see. What is address space randomization? ASLR. Processes have memory. Oh, neat. All of the memory addresses to each byte. What? This stops being like understandable English. I guess they're just saying every address refers to a particular byte in memory. I don't know. keeps us from knowing what memory addresses are for certain regions of memory. Yeah, so when you load your binary, the kernel is going to read through the ELF header, see the different segments, and it will assign addresses to those. It will put those segments, map them into your virtual memory address space for the process at different memory locations if you're using ASLR. So the binary itself will have some indication in the segment, what is it called? The program headers, I think, where that segment should be loaded in virtual memory for runtime. But with ASLR, they ignore that and generate a random base address, usually aligned to a page for performance reasons, and just map it in that way. And then the actual executable has to be compiled in a certain way so that it doesn't have any absolute offsets and like references to absolute addresses. It needs to be a position independent executable, and the libraries need to be position independent code as well, so that they can be placed anywhere and their references are all relative to the location where they were placed, rather than a location that assumes that they are placed at a fixed address. And yeah, but one of the things that you get around with ASLR is one of the ways to get around that mitigation is the fact that this randomization is happening on a segment by segment basis, or I think maybe on Windows they call it regions, but like it's significant chunks of memory are all, it's not every byte within that chunk that gets randomized where it's located. The whole thing gets moved to a particular place. So within that chunk, offset addresses are still valid to calculate. So if you can leak the address of one location within that segment, and then you have access to the binary, you can figure out the address of any other location within that segment, because it's gonna, like, everything within the segment is still fixed where it's at, which is ultimately necessary for the program to work in any reasonable fashion. You might be able to do a more intense version of randomization, but then you have like a lot more work for the loader to do something like runtime linking, maybe, where it's rewriting the program code based on the randomized layout that it chooses, or maybe some even more intense kind of solution. But realistically, you just have to have these different segments where everything within the segment is fixed and the location, the base address for that segment, is random. And don't leak addresses, basically. But when we get into things that have to get past ASLR as a mitigation, they're all going to hinge on the fact that the program somehow leaks an address, probably an address to libc or something. So once you have the address for the text segment, or the executable segment of the libc library, assuming it's dynamically linked in, then you can calculate the offset to the system call, for example, and then do your shellcode to return to there, or call that directly, whatever you need to do. I guess if you're doing shellcode, you've probably got an executable stack. You don't even need libc, because you can just write code that does a syscall. But maybe if you're doing a ROP attack or something. Okay. So let's see. They're just showing if they run the program multiple times in GDB. which is interesting because GDB by default, at least, is going to try to turn off ASLR. So I'm curious how they're seeing the impacts of that in GDB. Maybe the GEF sort of extensions to it re-enable ASLR, or turn off its mode or whatever flag it does, so that it never loads its binaries as with randomization of the layout. But yeah, they're seeing the stack layout being randomized here. That's all good. Oh, okay. They mention it, right? When you run a binary straight up in GDB, it can disable ASLR in certain memory regions. The reason why ASLR works here is I spawn the oh, I see. They don't really give their commands, so that's why. Okay. Yeah, so if you just run the process normally and then attach to it with GDB through Pwn tools or whatever, the program is going to have whatever its natural behavior would be if it was run, on the terminal or through some other mechanism, exec somehow, rather than started with GDB. So, yeah. So what is the bypass to the ASLR mitigation? They have to leak an address from a memory region that they want to know, where that segment has been loaded, what the base address of the segment is. You can look at the memory map. You can also cat proc whatever the process ID is /maps, and you'll get this printout as well, assuming you're not looking at it in GDB. Let's see. Yeah. The thing is, while the addresses in a memory space will change, the offset between the addresses themselves will not change. So if we leak a single address from a memory region that we know what is, okay, we can just add the offset to whatever address we want to know. We can find this offset in GDB, since the offsets between the two different memory addresses in the same memory region don't change. Yeah. There are different ways to get that memory address leaked, but it only applies to that one memory region. So yeah, if you leak an address in libc executable, in this one, for example, it's not going to matter for this one. It's not going to matter for these. It's not going to tell you anything about where the stack is located. Sure, and not the binary either. Okay. Okay, and then position independent executable. It's another binary mitigation, extremely similar to ASLR. Okay, that's not, I don't know, maybe I misunderstand it, but I think that PIE is the flag that you need to use for the compiler so that it compiles code in a way where the segment with that executable code can be located anywhere in memory and the code will still work. So it's a necessary precondition for ASLR to function properly and not a related kind of mitigation. In fact, I don't know what it mitigates on its own, except, I mean, maybe there's vulnerabilities related specifically to having absolute addresses, but it's more what's implied by the fact that you could have absolute addresses in your code. Yeah, so they're just sort of showing what it looks like if you were to compile that binary as a PIE binary, and you can see that the offsets, the virtual memory offset addresses, rather, the virtual memory addresses assigned to the text segment are effectively from 0 upwards. I don't know, maybe it's, a different offset than 0, but it's not the fixed offset of 400,000 or whatever it is, hex, yeah, which is what we saw before. This is what you would get when the code is definitely going to show up at that address when the binary is loaded, versus here, this is just the offset from whatever the base address chosen by the kernel is when it loads that segment. And yeah, we can't set that breakpoint, but you could say probably something like try plus that segment, or provide a memory map or something. I don't know. Okay. PIEB and PIE run commands. Oh, I guess there's additional commands in GDB. Maybe this is GEF specific stuff, but you can set a breakpoint given the offset from the segment base, and then when the binary is loaded and that segment and the memory layout is randomized, it will put the breakpoint at the correct location, which is nice. So you don't have to like start the binary, break on the first instruction, on the entry point instruction, then calculate what the loaded address of your desired breakpoint is, and then set the breakpoint. You can just set it up based on what you see in the disassembly listing, and it'll do all that for you, which is convenient. Yeah, you need to leak the address. Okay. All right, so now moving on to the next category of buffer overflows. Hello, Triple Dizzle. Thank you for joining. Honestly, this is the first time I've streamed and had anybody watching, I'm pretty sure. So, a little bit exciting for me. I'm doing some binary exploits using this nightmare course of, I don't know why they call it a nightmare, like, I think that's just the theming. I don't think they're intending to say that the difficulty is like a nightmare level. What is binary exploitation? So, as an overview, I guess, the idea is you have an executable program that's the binary in question. So it's not necessarily referring to the idea of binary numbers, because data in general in on a computer is going to be encoded in binary for the purposes of the physical processor. But in this scenario, we refer to the executable programs that are like machine code instructions to run on a physical processor or a virtual machine emulating a physical processor. We refer to those as binaries, rather than maybe source code or a script that would go to a virtual machine like Python or Ruby or something. And exploitation then is if there is a vulnerability of some kind, such as what I'm going through right now are vulnerabilities that are all considered buffer overflows. The exploitation is coming up with some kind of input to provide to that binary application such that you can control its behavior in a way that was not intended by the author of the program. So I can show you the one that we just did. There is a program called VulnChat, and this course is all very small programs that were written explicitly to have a vulnerability so that you could practice writing an exploit for them. And they're used in hacking competitions called Capture the Flag. So the fact that this is called VulnChat is like, you wouldn't write this program for your own purposes. This is explicitly to be hacked. So when I run the program, it asks me for some input like my name. So I can put in Hamlet. And then it's got whatever output, like I'm joining a chat room basically. I can provide a message and it says, no, that's not the right input to give, basically. The thing is, with this program, there is no correct input. There's no like secret password that I could guess. I have to discover an input that happens to exploit some incorrect coding in the program in order to make the program behave in a way that it was not intended to, but is doing what I want it to do. So if I send it this string of text, and there's a little bit of extra data after here that's not printed by cat because it's binary data, but these two lines happen to be, I guess in a sense, a secret password to tell the program to do what I want. If I hex dump this txt file, we can see it's got all those A's, and then the %53s is here, then a whole bunch of B's, and then a little bit of binary data, which happens to be an address of code that is in the program that I want the program to run. And if I put that address at this very particular location, along with all the previous stuff, then it forces the program to run the code at that location. So if I pipe in my exploit.txt, it gets this weird username, and then it will print out the flag file that I've set. And so it's basically like a kind of password, except to figure out the password, you basically have to do some reverse engineering on the program and understand enough about how the executable works and the behavior of a binary running on, in this case, Linux, to be able to work out what a valid password would be. Let's see. What do you use to practice that I would have imagined Parrot OS or Kali? I think those would be fine. Right now, this is just a VM running Ubuntu, because that's sort of what they recommended in the setup, I think. My main OS is Arch Linux. That's just sort of where I'm at in my life, I guess. But I don't think there's anything wrong with Parrot or Kali Linux. I have no actual experience with Parrot OS, so I can't really speak to that. I don't know if it's a flavor of Debian or Ubuntu or something. And I've only used Kali Linux a little bit, but I tend not to. I don't do a lot of like pen testing stuff. I've used Metasploit like 1 or 2 times in a CTF, and mostly the challenges that I'm most interested in are like reverse engineering and these binary exploitation things, where the tools are for this are definitely on Kali, but I don't need all of the other stuff. So I tend not to run that. I can just do a much more minimal thing, set up Arch and install like 5 or 6 programs. So I use like Radare to do the reverse engineering stuff. I also have Binary Ninja on my host OS. I don't have it in the VM because I don't think I need it for these very small programs. But if I need to look at the assembly instructions and have it in a slightly nicer view than what you have in GDB, then I can do that, and I can like browse around. And yeah, I'll probably end up doing that for the next challenge, just because I think this one I was able to get away with like basically, well, I did end up opening it once, but I think if I know what the approach is and it's a relatively simple kind of buffer overflow, then maybe I don't need to actually go through all of the process of reversing it in Radar. I spent a while doing that for the first couple challenges, which you can see on the earlier stream videos if you want to go back and watch those, and it just takes a while and doesn't end up being as meaningful as just sort of trying some stuff out and doing stuff in GDB. Okay, so need to make a new directory. It's 06 BOF shellcode CSOL 17 pilot. That way, yeah. What? Cannot. Oh, I need dash P. And I need 2 dots, probably. Yeah, okay. Then I'm going to copy in the binary from the original Git repository. Pilot. Is there a flag in there? Nope. Okay, interesting. Do you know how to pen test though if you wanted to? I don't know that I would go that, like, I wouldn't say that I'm very confident in that. So like I would be pretty certain that if I went and took like the OSCP or something, I would not do very well with it, because there's a lot of, I just haven't practiced it. I think I understand the general ideas behind what you're trying to do, but there's a lot of elements to it that are almost like things that you would know if you've done more sysadmin work. So my experience primarily comes from being a software developer, doing like some game development stuff. So I look at things maybe more from a programmer perspective, and knowing stuff like how to find password hashes and all kinds of other useful stuff in an Active Directory setup, and that kind of stuff is like not really my wheelhouse at this point. I'd like to say that I would have the confidence to, if I wanted to get that kind of certification and get that experience, that I could practice it and learn those things. But the times that I've spent towards that haven't been as interesting to me, I think, as learning some of these low-level details of how binary programs work. I end up learning a lot about the, like, I don't know, what are generally considered some of the most boring parts of like how the computer works. Like, how does the virtual memory system in the Linux operating system work? How does the binary loader code work? How does a linker work when you use it to generate a binary from a bunch of object files that the compiler has created? Those sorts of like very boring, I don't know, like underlying pieces, knowing the details of those and then knowing them well enough that I can come up with a way to subvert their behavior and control a program to make it do what I want is it's more like the learning how to do that stuff that's really exciting than the like actual end result. And I think a lot of the pen testing work is the fun of it comes from the end result of like, okay, I have scanned these systems and found them to be vulnerable to this or that particular known exploit. Almost never using it. You're not using a 0-day in a pen test, I would assume. If you have knowledge of a 0-day, you should be reporting it somewhere rather than using it to get into a client system and show how cool you are. But yeah, so you're using some known exploit, presumably finding an existing proof of concept kind of thing that you can plug into Metasploit, and then just pop a shell basically and see where you can pivot to from there and get whatever access will look most problematic to the client. I think like what they would be most concerned that you happen to find a way to get access to. And if I've done the same process on 3 previous clients or something, like, oh, they're all vulnerable to this one particular bug, and I just it was the same sort of thing for each one, that I don't feel like I would be learning much. And I think from my experience, that's where I get kind of bored pretty quickly. Similar kind of thing to maybe doing bug bounty is like I've tried to look into that, and just I don't know. I think maybe on the bug bounty stuff, it's more like the amount of time that I need to investigate to be skilled enough at it is really poorly. Like it doesn't measure up very well with the fact that you're in a race with everybody else to get any kind of cash, and if you aren't the fastest at it, then somebody else is going to get that bounty before you. And if I'm completely new to it, it feels like I'm like starting in the worst position to be able to actually succeed. Which is, that's probably overstating the problem, because there's definitely a lot of stuff out there, but it's really about being able to find stuff that other people haven't found in terms of vulnerable systems, let alone the actual bugs. And I don't know. I don't think I had much success with that in the little bit of time that I spent on it. What programming languages do you know? A lot of, again, like, what do I know versus what have I written code in? I've written code in C and C++, a lot of C++ code in game development. I've written code in Python and Ruby, written code in like Lisp or a couple different flavors of Lisp, Java, C#, stuff throughout the whole gamut. I don't have a lot of experience with some of the more academic languages like a Haskell, OCaml, those like more very strongly functional languages, but I'm certainly interested because they are such a different approach. Yeah, Python's a great language to learn. I would encourage going that route, especially if you are interested in any sort of infosec hacking kind of stuff, because Python seems to be the preferred language for people writing tools in this space. Being able to read the code for the tools that they write, I think, is going to be really helpful to you. Yeah, so I think Python for doing pen testing is an excellent choice. It's definitely a great choice of language to get started with regardless. I had done a lot of coding before, but I took a course. Well, it's weird. I learned this. I picked this up when I was taking a course that was using C# as the language, but I found somebody had written a sort of Python knockoff almost that worked on the .NET VM way back in the day called Boo, and that was the first language that really unlocked my excitement about programming, maybe since the first thing that I ever did with programming, which was like QBasic in the 90s. Like, yeah. So Python can be a really enjoyable language to work with. If you watch this stream, you might see me get frustrated with some of the things that I'm trying to do with Python just because of a very minor kind of issue with the way that the encoding stuff works in Python 3 versus how it used to work. But overall, I think it's a great language. Ruby is, I guess, what's used for Metasploit. So if you wanted to read through somebody's like Metasploit module for a particular exploit, then knowledge of Ruby would be helpful there. But otherwise, it's probably not going to come up. Yeah. So good luck with doing the pen testing work. I can definitely recommend some other streams of people that are more experienced in that if you are interested. What I would suggest is, let's see, Sherlock Sec, I think, is a cool guy. He does a lot of stuff on Try Hack Me and maybe Hack in the Box. They seem to be doing a lot more with Try Hack Me these days. Maybe the people that created that are like trying to push the streaming angle a bit more, because I think Hack in the Box, you're not allowed to stream a lot of the challenges that they have. And then I would also suggest, who is it? Optional rather, who also does a lot of Try Hack Me stuff, and they seem to be more knowledgeable about yeah, you can only stream the retired ones, and I think there's only like a couple of those, whereas Try Hack Me is like stream whatever you want, and which, I mean, I get the idea of not putting the answers to stuff out there, but unless it's a test that you're using for giving somebody a certification or, you know, some result that requires the integrity of the results of that test, like, let people explain how they did stuff. Let people give the video of them going through it, because it, you know, it's up to each person whether or not they want to look at an explanation. Like this whole sequence, this whole course of binary exploitation stuff that I'm going through has walkthroughs for every single challenge, and it's kind of just up to me whether or not I want to read that walkthrough and use that to solve it, or if I want to work on it without knowing anything, which I think allows me to set the challenge level for myself. So I like the idea that Try Hack Me is doing their you know, streaming oriented kind of rule set. And yeah, I think Optional does a lot of King of the Hill, which is a interesting twist on maybe the more pen testy kind of stuff, where you get into the box using some exploit. It's almost always a web based exploit, and then you have free reign to try to like take over the box and retain control over it, while other people in the, you were paired up with like 4 or 5 other people, and they are also trying to get into that same box and maintain control over it. So you can do all sorts of fun tricks to lock them out or trip them up or whatever, and it really starts to, like, you know, let you play around and find out how deep you can get in terms of using the Linux operating system and all the tools that it has available. I've definitely thought about playing that, but almost all the time my thoughts go to like, well, can I write a program to do some really devious thing? Like there's a text file that you have to put your account name into that's the, like, if you have your name in there, then you are the king of the hill. And so I keep thinking about, could I write a thing that makes it so that other people think they've written their name into it and it fakes to them like that worked, but really it's only my name that's in there. And I just, you know, at some point I start to realize like, well, mostly what I'm interested in is like writing some code rather than actually going and winning at any of those competitions. And I wouldn't want to do it in a way that makes it not fun for the other people playing, I think. And I can come up with a lot of things that I think would be not very fun. So I don't want to get into that route, but maybe at some point. So yeah, those are 2 people that I would recommend. Got a lot of other people that I could. Nahamsek, you've probably heard of him because he's got, I don't know, tons of followers. He does a lot of bug bounty stuff that's almost all like web exploitation work. Dowright is pretty cool. I don't think that he does any pen testing stuff. He's mostly what I've seen working on a really involved firewall that you can set up for yourself. And John Hammond, probably also know of him. Yeah, the DNX firewall. Yeah. I mean, he's a really cool guy. Like, even though I have not set up the firewall, and I don't know that I ever will. I think he's just really a fun guy to talk to, and he knows his shit really well. So I've, been able to ask him questions and learn some stuff. John Hammond, probably know who that is just because he's got 1 million YouTube videos and it's got a big following on there. I'm not necessarily like, clued in with everybody that's on Twitch that does this kind of stuff. But let's see. I'm trying to remember who would specifically be more in the pen testing stuff because I follow a lot of people that maybe just do like, I don't know, hardware hacking kind of stuff or other programming stuff. Obviously, Live Overflow. If you don't know who that is, look that up on YouTube, and lots of really awesome videos that he makes, like well done videos, very informational. Yeah, a lot of programmers in my list. Who else? There was somebody else. Maybe I just don't follow him, and for some reason I haven't clicked follow. But Nahamsek had one with the Cyber Mentor, and I've heard really good things about the Cyber Mentor. Oh, there he is. It's just up here. Follow them as well, I guess. Yeah. That's what I would recommend from who I know. And if you know of anybody, I'd be happy to check them out. Don't mind having more people to watch on Twitch. Although I'm also like, when I spend a while watching stuff on Twitch, then I'm just like, oh, I should be doing stuff, like practicing. And so I tend not to end up spending as much time as I could be learning from other people on Twitch because I get too, I don't know, ADD or whatever, and like I want to start working on something. So, okay, gonna get back into the actual practice, and we've got another binary to work on called pilot in this case. And so we can see what my process is. There's no flag file, which is interesting because I know I'm going to, just based on the name of this folder, shellcode, like I need to generate a shellcode, which I'll use Pwn tools to do, and then provide that shellcode to the program, and it will use it to, I'll run my shellcode, which will probably spawn a shell or something, thus the name shellcode. And I don't know what I guess just spawning the shell should be enough that I know that I did the exploit, basically. I don't need an actual flag file, but presumably in the CTF itself, there was a flag file that you would find and read and use that to, get the points. So let's just run pilot. Welcome, dropship pilot. I am your assistant AI. I will be guiding you through the tutorial. As a first step, let's learn how to land at the designated location. Your mission is to lead the dropship to the right location and execute a sequence of instructions to save Marines and medics. Okay. Good luck, pilot. The location, and then it gives me an address, which is convenient. So that, based on how that address looks, I'm gonna guess that is a stack somewhere within the stack, basically. Which makes sense if I need to put my shellcode on, like I need to input shellcode and then overwrite the return pointer so that I jump to my own shellcode on the stack. It's very helpful to have an address on the stack that I know, because otherwise I'm sort of guessing at the return pointer, just sort of trying to work out like what address we should be jumping to. And because I have turned off ASLR on this machine, it is not the same, or it is the same address every time. So let me turn that back on. And let's see if that impacts anything. Yeah, so now we're getting the random stack address. So I've made the challenge a little bit more difficult, but since they print out a location, like they just leak it directly to me, really I just need my exploit code to read that value and then calculate a good offset from that location. So that should be fine. Right? It's different every time. Okay. So I think the first thing I want to do is open this up in Radar. Oh, good night. Thanks for coming by. And yeah, have a good night. The first thing I'm going to do is open this up in Radar and see where on the stack this printed out address is. Maybe it's just the address of some buffer that they've allocated for the command, and that would be convenient because then I can probably just use that address directly. Yeah, let's find out. Okay, using C++, so we get nice long function names. So we set, I don't know, an empty buffer on standard in, standard out. That's helpful. And then we use cout to print that text. And we have one variable on the stack in this stack frame at RBP minus 20 hex. And that is pretty sure, yeah, so that's the address that we print out, is just, and that is then also where we read into. So that is convenient. We just need to and if we put in a command, it doesn't, it just exits anyways. Okay, so we know that the address that is printed out is the beginning of our command buffer. And so that's the address that we need to overwrite into ret. We are reading 40 hex bytes. So we have an overflow of another 20 hex bytes. And I think our return pointer is going to be 20 plus 8 for the pushed RBP. And then the next 8 bytes will be the return pointer. So let's give that a shot. And we need to put our shellcode in those 20 bytes. Is that true? That seems annoying. Maybe we could, I mean, let's find out how long of a shellcode we get from Pwn tools, I guess. What are the commands? Pwn, shellcraft. Did I do it that way? Okay. We want, let's do raw output, and the shellcode that we want is let's do -L to list the shellcodes, and we want we have nothing. Okay. Script Linux. So it's AMD 64 Linux bin sh. No, not bind sh. Just .sh. So use this one. So I'm going to output a shellcode in raw bytes for AMD 64 Linux sh, and then I'm going to just count how many bytes that is. It's 48 bytes, so it's a bit longer than we really want. Could we do I386? That's a little slightly shorter, but not short enough. How to do this? We could definitely have it like jump, so we could split it into two parts and jump over the return address. But some of it's going to be overwritten by the remainder of the code in that function. That's my thinking. Maybe I am making this more complicated than it needs to be. I mean, again, without a like flag file, I wouldn't think that the shellcode would be read a file. Could be. But I also don't think that read would be any shorter. Is that what? Oh, maybe we need MD64. Interesting. All right, so now read doesn't care about byte, like it's not gonna end with a null byte or anything. So should be able to, we might be able to get a shorter one just because we can provide a null byte. How do I tell it to not care about like I can tell it to avoid new lines and avoid null bytes and avoid specific bytes, but I don't see any reason, any way to say don't avoid anything. Can I give it a value that is unlikely? It's not, I mean, that's not unlikely, but what am I doing? Yeah. Well, let's look at the shellcode that gets created. And see if we can make it shorter somehow. Like we might be able to get rid of some of these. is there potential to call system? We need to know the address of system though. So that doesn't really help me. Right, what is the length of like cat? Doesn't seem like it would be any shorter. Oops. It's a little bit shorter, but again, still doesn't really help me. So right. 40 bytes with are we pushing anything to the stack or otherwise writing to the stack? What is this? It's just tabbing between them. Okay. Doesn't look like we are writing to the stack anywhere. So I think we can assume that our shellcode is not going to be overwritten to. And so we can use all of those bytes, but we would still need to jump over the return address, which is going to be at 28 hex into the buffer. Okay. So let's try that. So I put the shellcode in a file, and I'm going to just take a wild guess at where we're going to be, you know, less than 20 bytes. I guess what I could do is so we've created a part 1 shellcode. I do where do I read in from? So I want to output raw and then input from that file. Do I need to set the context? Yeah. And we want AMD64. Let's say Linux / AMD64. Or I'm just going to say AMD64 since Linux is the default. Okay, so that's 30. So that should be fine if we break there. And we put a jump after it. And then we have put the address in here and that should be a quad word. I think DQ is the right thing. We'll find out. Oh, and that's going to be annoying because I've enabled ASLR, so I can't just hard code that in. We'll have to put this into our exploit script. Okay, so I put a label for part 2, which will come after these bytes. Let's put 0 there to begin with. Say I don't know. When I put this, okay, so we'll see what the length of this is. This gets more tricky than I would like to do, but basically we have a quad word here. This should calculate an address as an offset that goes beyond that quad word of data. What do I do wrong? What did I get wrong? There's no DQ. I guess I could put it as bytes, but I should learn how to write assembly a little bit better. Data representation. Like maybe I should look up the assembler, and maybe that's what. This doesn't seem relevant. Oh, using that. See, the problem is like so much of this is just going to be, I don't know if it's using. Can you show me? So we look in here. There's no mention of DB anywhere. .word, huh? Maybe the DB stuff is just with like NASM or something. They have .quad then? Let's see if I can do .quad instead of DQ. What? Oh. God damn it. Well, that's fine. Okay. Still a bit too long, huh? What if we move the jump? $38. Then we need another. Oh wait, 40 is the length that we want because the address starts at, no, we want the length to be 48. So we want the 8-byte address to start at 28 hex, which is 40. So, okay, we need to move instructions up. Let's try that. That's not what I wanted. No. God damn it. I don't have. Alright. Let's generate that shellcode again. Where did I have it? Let's try here. 44. Yeah. Might be 3. I mean, at some point I can just pad it. Let's just do that. Really? Okay. Oh yeah, we were at 44, so I need another 4 bytes. What the fuck? Now it's aligning shit, or... just do word. Can I do 2 different zeros? I think I can do that. We'll find out. No, does not like that. Just really getting questionable with my coding choices. Okay. So at this point, look, we've got 4 bytes of padding, 8 bytes for where the address will go. Good. And then the whole thing, I've got more. How do I do just object dump some raw assembly. Maybe there's like Pwn tools, disassemble. Do we have a flag? Can we do this on the command line? Maybe there's this as. All right. So let's output this in hex. And then context is AMD64 and okay, so that jumps 30 or 2 address 30. Chaz add RSI RSP. Let's double check. Yeah, okay, all right. Seems like that might work. We just need to be able to insert the address here as, let's see, can I do like of course it's gonna treat it as nonsense, but okay, and then yeah, we get our address in there. Excellent, excellent. So let's see, we can just sort of insert we want so this will be our shell code, but we need to do something like that. This is where my Python knowledge gets a little bit rusty. Line string with format. Is there anything necessary? Do you just call, you could use an F string? Do multi-line string literal. Does F string support multi-line? Multi-line F strings. Okay, so I can just use F instead. Cool. And then put in, interesting, I like it. I forget what the format syntax is. This is one thing that is much nicer in Python. They sort of, I wouldn't say they took anything idea-wise from Ruby, but they, they certainly are in that same realm, and frankly, they are more advanced in certain ways just by having like shorthands for the like I would call this bang R, but you can think of it however you want. Can I so it's just those three options, I guess. And if I want to do hexadecimal format specifier mini language, type X, I put the 0x in front of it, I guess. Let's try that. Let's do like alright. I have to put it with a colon. Or does it explain it here? Oh. An F expression can be whatever, and then a colon in the format spec. Okay. So let's do that. And we'll say ret adder equals and our set to an F, and then we'll print the shellcode just to see what the situation is. Why do I have it twice? It's not what I wanted, but this is certainly working for me. Oh, of course. Put it on the wrong thing. All right. So I think we are in a place where we can start to write our exploit. What we want to do is open the target process. So it's called pilot. And we'll receive until location. And then the return address is going to be an integer conversion of target. Receive line keep ends is false. Interpret that as 16 like as hexadecimal, base 16. And just see if this works. Okay, so it gets the address in there. Cool. Then I want to look at the assemble. How do I set the context? I know there's like basic way to set the context. What else do we have? Arch. OS, maybe. Linux, okay. So then the ASM stuff, we can send it shellcode. So we'll compile the shellcode and we'll send that. And then we'll go interactive. Interesting. Nope. Okay. Well, that is annoying for sure. See, what I would want to do is print out do we even need to send it as a send line? Probably not. But I don't know. Just in case. Still don't think it's gonna work. Yeah. Oh, okay. Let's try it that way. Okay, but I don't have a flag file anyways. No, we got the sig fault. See, it would be nice to be able to do this, but I just don't know how to get that working. Like, maybe I should read about it. Because I don't know that I can just manually do this in GDB, given where was GDB? Given that I need to read that, generate shellcode, and then send that. I could try strace, but since I'm running it through Python, it's going to be incredibly noisy. So what do I want to do? I want to maybe I do. It says it's a tube. Oh, because it's. Is that helping at all? Doesn't seem like it. Need to. What? There's no. Okay. Alright. I guess it's been stripped. Of course you're not gonna tell me though. Okay. I don't think this is gonna work. Oh, and I don't want to actually. I guess I did want. This address, but it's not going to be at that location because it is our. Can we do it that way? It's just AE5. No. Oops. Is that? How do you list the breakpoints? Info break. No breakpoints. Oh, okay. Alright. Doesn't help. Great. What the fuck do I need to do? I don't think this is gonna work, but we're gonna try it anyways. Yep. Doesn't matter. Okay. I don't know how to get GDB working, so with Pwn tools, so let's try it with strace. Hmm? What the fuck? Alright. Yeah, just deeply annoying amount of stuff. So where did we go wrong with? a seg fault somewhere. There we go. Oh. Alright. Get an address, seg fault at none. Cool. Again, very unhelpful. Did I ever check the security? Okay, so NX is disabled, so we definitely can execute the stack. All right, let's try this. So if we take out this one, how long is the first part? 47 bytes. Okay. And the first thing we will do is int 3. Just run that. Can we? No. We did get the signal, the trap signal. Okay. That is good. So then does it tell us the address where we got the trap? No. It's too bad. Although if I run it in GDB, why don't we? Okay, because GDB is gonna turn off ASLR, I think. We're gonna get the same address every time. Okay, cool. So I'm going to create a special version of the shellcode. With that address in particular instead. We'll see. That should be short enough. Yeah, it's 1 byte shorter than, okay. I mean, Hell, that could be the problem, is that we're still running up against the limit. And we need to take out that padding. But we have 40 bytes to overwrite, so let's see. Get that address in there. All right, let's see. Okay. We're doing a move ABS. Oh, that's fine. That's not move APS. But right. So we're getting the int C. But why is the trap? Oh, okay. It's just not. It just gets confused, I guess. Like. Just like disassemble from there. Why do you want to be like that? Okay. So yeah. So let's see. Let's step one at a time. Now we've got bin SH on the stack. And RDI has stack pointer, or pointer to that string, I guess. Well, maybe something is going wrong here, because this is not what should be the case. Yeah, okay. We're getting something wrong after this stuff. What is this push? Well, why does that become? Oh, right. Okay, so we need to move the stack pointer because now we're writing into our own shellcode. Okay. So doesn't really matter, I don't think, how much space we give it. We still need to see how long this is. What now? Junk at the end of the file. Oh, sure. now we are too long. And that would probably change the padding here anyways. So we can take out a word. We still gotta see if this is too long. So that's a fine length. And that is 1 byte too long. Look at this. No, doesn't like, right. Okay, but I think what we can see is this is still where our, why do we have 2 bytes here? Because it really should be, right? That should be 48 bytes there. So why does it print 2 no bytes? Let's see what the full assembly looks like. Yeah, we're good. And we just got the 1 null byte. Well, we can try it out. Hey, it worked. All right. I feel good about that. Yeah. We get the shell. This is my, I like this stuff a little more than the earlier buffer overflows because this feels like a real scenario. Granted, there are probably programs out there that have a system call or something, but like it's unlikely that they're going to call system and just spawn a shell. Maybe it's unlikely. I don't know. Maybe that's more realistic than I'm thinking. But the fact that I can do this and handle the ASLR mitigation with it because it's direct. I mean, that's not a difficult thing to handle because it is just directly linking or leaking that stack address for me. But anytime I can get shellcode to work, I feel a little bit better about how I have, what I have managed to do. All right, let's read through the walkthrough, see how much easier it could have been than whatever I ended up doing. Especially with putting the jump in there. I guess that didn't end up being all that tricky. It wasn't a source of problems, really. It was the need to give myself stack room that was tripping things up at first. So they run the binary. They see, gives you the location. Okay. So we can see that we are dealing with a 64-bit binary. When we run it, we see that it prints out a lot of text, including what looks like a memory address from the stack memory region. It then prompts us for input. Looking through the functions in Ghidra, we don't see a function labeled main. However, we can find function at that address, which contains a lot of strings that we saw the program and output. Yeah, that we saw the program output, and it looks like we would expect to see. Or it looks like what we would expect to see. Okay. Prints a lot of text. Sure does. However, there are two important sections. The first is where it scans in the data, calls read with a size of 64 bytes, and we can see that the buffer that it's reading into can only hold 32 bytes, so we have an overflow. Also, we can see that the address printed is an info leak. It's information about the program that is leak. Okay. Yeah, I mean, it's printing out the stack address for that buffer. So, or just the memory address where that buffer is happens to be on the stack. Looking at the stack layout in Ghidra, there doesn't really look like there's anything between the start of our input and the return address. With our overflow, we should be able to overwrite the return address and get code execution. Let's find the offset between the start of our input and the return address using GDB. We will set a breakpoint for right after the read call and look at the memory there. What did we end up doing? I think we just calculated. Yeah, I just calculated it from the size of the buffer and the fact that there were no other variables identified in radar. So that's fine. You can see that the offset between the start of our input and the return address is, those addresses is 28 hex bytes. So we have a way to overwrite the return address, place to store our shellcode, and we know where it is in memory. With this, we can write our exploit. So they have what is presumably a much shorter shellcode, and I'm curious what their shellcode is, because the Pwn Tools default shellcode is longer than that, and that's what caused me to need to try to do the jump. Oh, this is like the original write-up, I guess. Oh, diagrams and everything, nice. They have 24 bytes of shellcode. They have such a short shellcode that they needed to pad it out. What is their shellcode? Do they have... They don't list the assembly for it, I guess. Alright. Well, let's pop it on into... Can I do... I probably can't do it that way, huh? Let's look at the hex for it. Yeah, okay. So, how do I want to do this? Okay, so I just put the G on there. So I'm gonna do like said. I guess I can do it that way. There we go. And what do I need to do? Oh, it's this SM. Okay, so they what is their thing doing? Clear out ESI. They move the string into RDI, which I guess, I mean, this doesn't look like it would be. And then they, oh, interesting. So that's the negative version of, I guess, the string for. Does this just have to assume that EAX is 0? I wonder if this, I mean, presumably this shellcode would work. Let's give it a shot. I just, oops, I don't want that. So what do they need to do? They write theirs, and then they put the input address. I mean, I guess let's just go with this. What if I pasted something wrong? Oh, well, that's mine. Sure. Really? Oh, do they have a... Jesus fucking Christ. Why do I need an empty string to start it off? And that segfault, that did not work. Interesting. Let's try to put a trap in front. No. Didn't hit that either. I don't know how much time I want to actually put into figuring out why their shellcode doesn't work, or why their exploit in general, I guess, not necessarily the shellcode itself. Yeah, and I guess I didn't need to do send line, but it apparently didn't end up mattering. In their payload length, right, should definitely be less than 40 bytes. Where do they print that out? It's exactly 40 bytes. Interesting. I guess it's 40 bytes width. But they, on the... Is this one longer? Looks like it's the same sequence. They have 4 bytes of NOPs. Like... The encode causing it to be longer? Is that the issue? Yeah, okay. Oh. Okay. And it still segfaulted. I don't know. I'm not gonna... Maybe I'll come back to it, but I mean, I would be interested to know how they're able to get away with such a shorter shellcode, because they're calling 0x3b, which I think is yeah, it's the same syscall that we're making, but in ours we needed to set up like an array of pointers, and I didn't necessarily see anything of that nature. So we push the string, we generate the string that is the like bin/sh, presumably, by doing this and then negating it, which helps maybe with null bytes, for example, the null byte here. And then multiply by ESI. Oh, that might be how they're clearing stuff out, because it's 48 F7. Let's see. So it's probably this one, and that is going to clear out RDX and RAX, which I guess are where the other ones. Oops. Well, okay. So that's why the AL can just have that added to it. And then, yeah, that's convenient. Okay. So, yeah, that's a smart little shellcode. I'm a little surprised that they don't have anything that short in Pwn Tools. But I think my understanding of what's going on with this is we clear out ESI. That'll be useful later. Then this sets up RDI to have the string /bin/sh0, right? Which is, yeah, and maybe there's 2 slashes in there or something, but that should be, the whole string can fit in the register. And so that's in RDI. Then we use the multiply with ESI. So we're multiplying by 0. So the end result of the multiplication is going to be 0. And the way that works is we end up setting both the RDX and the RAX registers with the result of that multiply. This is like the lower half, this is the upper half, because you get a 32 byte, or I'm sorry, a 16 byte result, a 128 bit result. So ESI, RDX, and RAX are all 0 at this point. Then we add to AL the 3B for the syscall number. Then we push RDI, which had the string in it. So that's on the stack. Then we push the stack address. Then we pop that into RDI. So now RDI points at the stack address with the string. RDX is 0, which is the second parameter, is my recollection. And RAX is the syscall number. And that's what we end up setting up here. So RAX has the syscall, EDX or RDX is 0 here, RSI points to, they're using RSI here rather than RDI. I don't know how much that matters. I don't know. I think they're taking advantage of the fact that okay, I think this is just trying to be a little more like, so I guess we have the last pointer is null, but this one is pointing to an array of the parameters for the program, whereas I think in their version, the argv is also a null pointer. So these last two parameters are null pointers, and we just have a pointer to the string, which is not necessarily how you're supposed to do it. How to say it? It is not necessarily how you are supposed to call the exec VE syscall. I think you, by the standard at least, you're required to set up this array of the parameters, with the first one being the name of the binary. But I guess it works if you have it as a null pointer, because I think that's what they're doing in this very short shellcode. So that's cool. Yeah, and that certainly makes it easier to do this pwnable. I don't know, this thing doesn't give you any instructions around how to create a shellcode, and they give you, as a first challenge that involves a shellcode, a very short buffer in which to insert shellcode. Like, as far as I can tell, this had to use, several tricks to get a incredibly short shellcode that spawns a shell. Which is, I don't know. I mean, it's a good challenge, certainly, but if you're not experienced in writing shellcode, I don't know how you would have come up with that one versus like what you would get by using a tool that generates a shellcode. I think I would have had a fair bit of trouble thinking up and coming up with a shellcode quite that short. And they still, and I understand assembly, I think. I don't know. Anyways, enjoyable. Let's move on to the next one. So, let's see. We've got we've got two more shellcode challenges. We'll see if I can get through both of those today, and then call that an end for the stream, because this is already possibly the longest stream that I've done, and I'm sure that it's going to be another hour, maybe 2 hours before I'm through these other two pwnables. But I think that'll be good progress, and we'll get into some other categories that I have not necessarily seen before, like a static buffer overflow. I don't know what they mean by static. And then dynamic, I also don't know what they mean. So these are going to be probably the most challenging, because unless it's just a name for something that I have seen before and I can't quite grasp what they're trying to get at with the name static or the term static, I'm going to be, a little bit out of my depth. These other ones, I have done buffer overflows like these before. Done a shellcode and done return pointer overriding, like that kind of stuff. But then we get down here, I don't know if I've done it before. And so doing it without the walkthrough is going to be tricky, I'd say. It's going to, I feel like I'd be lucky to get one of them done in a given stream. And then it just gets more and more complicated from there. But that's what the practice is for, is to get better. Never going to end up going to pwn to own or something without it practicing a lot. All right, pwn 3, Tamu 19, pwn 3. And I should really start to use these skills at some point on CTFs live. I mean, I do the occasional CTF, but I'm usually first off working entirely on my own, because most of the people that I know, most of my friends online that would be interested, even vaguely, or that, you know, work with computer stuff, are programmers that don't really care about any kind of hacking stuff. Yeah, I don't know. I don't get the like caring a whole lot about programming and then not at all about the cool stuff that you can do with hacking to do programming, you know, or extending your knowledge of programming into the realm of hacking stuff. But it's just not interesting for them, and I've tried several times to get them to join me in doing some CTFs, and for the most part, there's very little interest. Maybe some cryptography stuff or whatever, but none of this stuff. So I'm usually just doing CTFs on my own, which means I get to like 1 or 2 challenges in the whole time frame of the thing, and you know, there's only a few, and I'm usually doing the easy route kind of stuff. So I should practice on those as well, because eventually I might be able to do some of the more difficult ones while the CTF is going on, and that would be pretty cool, just to be able to say I got some challenge that, you know, only a handful of other people got to during the CTF. Right. 06. Yeah. Are there any other files? No. Okay. So I guess we don't have flags for this category because we're just going to pop a shell, and that'll be it. 32-bit binary, and yep. It's PIE, but NX is disabled, so yeah, that's necessary for shellcode kind of buffer overflow exploit. And I guess ASLR is going to be on. Hopefully they'll leak an address for me. Let's run it. Yep, there's that. There's a useful address. It doesn't look like it's a stack address, but it's an address of something. Okay. Let's find out what it's an address of by checking it out in Radar. Okay. Oh, here's the thing. So I was confused around this stuff in the first stream that I did where I was going through these challenges. And I ended up afterwards reading up on it. And it's just a way to get the address of program counter, so thus get PC thunk in 32-bit when you do PIE, because there are no instructions that work relative to the instruction pointer register. You need to do something or other. Why does this not work? There we go. To grab you need to be able to do something which loads the instruction pointer address, the same address that the instruction pointer would have at least, into a register. And so they get whatever. So if we call a function and then we take the top value on the stack and put it in a register, that's going to be the return address for that function, which once we return, is going to EAX should be the location of the add instruction. And then we add something to it to get, I don't know, some fixed address, I guess, such that we can continue to use it. Honestly, I think maybe, yeah, we just use it in a couple places maybe, and that's why we add this to it right away. So let's see what is going on in the function. We have our prologue, push some registers that we're going to use, get that address. Oh, maybe the stream cut out for a second. But yeah, I'm just reading through the assembly for this, and we are gonna pull in some fixed location relative to wherever this segment gets loaded, and we use that. We set the vbuff. And call the echo function, which seems like it's probably got all the actual interesting logic in it. There we go. All right, and this is the same kind of thing, but it gets it into EBX instead of EAX. So this will be fixed location. This is pointer to some string that we're doing with printf. Okay. And so I guess we are getting the address of this variable in the stack in this stack frame. And then we call gets to read into there. Okay, so it's actually the same kind of challenge, but we have quite a bit more space to work with. And we're calling gets so we can write as much as we want. Yeah, seems pretty straightforward. I guess the reason it didn't seem like a stack address is I was just thinking in terms of 64-bit, where the stack address is going to be, 7FF something, probably just because you're up against that boundary, maybe. I don't remember, but it's a much lower number on 32-bit, clearly. Okay, so they leak us that address, and then we can write our shellcode to it, overwrite at, let's see, we push just one thing, so we have 12A plus 4 is going to be 12E. Yeah. So 12E hex bytes before getting to the return address. And let's try it then. All right, I'm actually going to copy the exploit from the previous one, because I think we can get away with using the same shellcode, and we'll need to update these things. We have to figure out, I don't think we need to break it up at all. So I'm going to take all that stuff out. And then our payload is going to be, let's do NOP sled. Doesn't really matter too much, I think. And let's see. Can that work? I feel like the encoding of it is going to make it all wonky. Okay, and then and we want to pad it out afterwards to all right, so the idea here is we will receive until whatever. I don't think we need to receive anything after that, actually. Then we'll get the address. We might have to receive until a explanation point, if I recall. We'll look at what the output is again. So then we'll get the address into there. We'll have our shell code, which we assemble with a bit of a NOP sled in front. If necessary, I could put a bunch of NOPs in front of it. Let's do it that way rather than deal with potential encoding weirdness. Okay, so we'll do a bunch of NOPs in front instead before we assemble it. Then we're going to take the length of the assembled shellcode, subtract the size of the buffer from it, and add the difference as padding before we write the address, so that we're writing the return address to the right location, which should get us the address to the beginning of our NOP sled. Yeah. All right, so yeah, we need journey space, and then we'll receive until the exclamation point. Let's see what happens when we. Okay, it doesn't like key pens. Yeah. Let's look at polib. Oops. I think I can probably get rid of a bunch of these. Yeah. This was from last stream. Okay. are there parameters? When they say drop the ending, do they mean the delimiter? So we'll find out. Okay. Alright, didn't quite work. By which I mean it didn't work at all. It's really the scenario that we are in. It either definitely works or it doesn't. So if we run this in GDB, we get the same address every time. Okay, so you can just what am I doing here? Okay. So I'm going to write out the payload file. And we will fix that back to what it should be. Okay, so now we have our seg fault. Because what happened? How do I put that again? Oh, let's look at it this way. Okay. It doesn't look like it's instructions. Oops. Let's go ahead and put three instead of those. And okay, I need to oops. Okay, so we need to modify that again. Okay, so we did jump into the buffer. How many did we put? 219. Okay, but our shell code, what is this decrement EAX business? What is that about? Forget how to reference RIP. About 48. So CC, and then we've got 48. 83 EC. Oh, you know what? We are assembling it as 64-bit. Thus the 48. That might do it. And then I should just straight up get rid of this, because that's all 64-bit code. And let's do .linux.sh. What did I forget to do? Is it a string? Oh, I want shellcraft. Okay. Let's see if this works then. Put it back to being a nup. Yeah, sweet. All right, that one was a lot easier, went a lot smoother because it's basically the same problem, and didn't have to deal with a really short buffer for the shellcode. And I already just decided to throw something in to give myself stack space for the shellcode's pushing of stuff, which didn't come up in the shellcode that team had developed in their walkthrough of this problem, because they did wherever RSP was, it's either in the padding or it's in the NOPs, and they only pushed like one thing onto the stack, so they weren't hitting into any of their own shellcode with those pushes. Cool. What is core? Is that from the dump? I guess so. I didn't intend to copy that over, because I remember there was a core in right? Oh, maybe it was in the earlier one. I guess the core is just, yeah, from us doing the getting it to crash. All right, and that's probably for my own setting. Cool. So let's see. Walkthrough should be very similar. 32-bit binary. It's very similar to the previous challenge. When we run it, it prints out what looks like a stack address and prompts us for input. When we look at the main function in Ghidra, we see this. Does the PC thunk, sets the buffer. Sure. And it runs the echo function. And yeah, we can look at the echo function. Has an input buffer of 294 bytes. Runs printf to print us the address of that buffer. and then calls gets to allow us to overflow the buffer. So we can see that this function prints the address of the character buffer input, then calls gets with input as an argument. This is a bug since gets doesn't restrict how much data it scans in. We can overflow, we get an overflow. With this, we can overwrite the return address and get code execution. The question is now, what do we call? There aren't any functions that will either print the flag or give us a shell like in some of the previous challenges. We will instead be using shellcode. Shellcode is essentially just precompiled code that we can inject into a binary's memory, and if we redirect code execution to it, it will run. It will need to match the architecture, so we will need to have ARM for x86 Linux. What? Need to have ARM. Oh, I think they mean ASM. They just typoed that. Okay. Whenever I need just generic shellcode, I typically grab it from shellstorm/shellcode. Yeah, that is a valid place to go grab some shellcode. Often a good idea to know what your shellcode is doing before you just throw it in there, but if you've got 23 bytes of shellcode, it's not like it's going to be opening a pipe or opening a socket to some random server and sending your data. The 23 bytes is just not enough code to do that, I'm pretty sure. No matter how tightly you squeeze in stuff. And maybe that 23 bytes of shellcode is like what they were using on the previous one, because theirs was pretty damn close to that length. Well, this is the 32-bit one, anyways. But it is, it's pretty similar. It doesn't do the multiply trick, and it has to do 2 different pushes. But sure, you can get a real nice short shellcode from Shellstorm. You can use Pwn tools to give you shellcode as well. And then, just to complain a little bit more, we have a similar situation to vulnchat. Or no, was it just get it and warm up? So warm up is the first in the category of call function buffer overflows. And they tell you how to do it in the walkthrough, but they don't really explain, they just straight up say, after we write 64 bytes, we overflow the buffer and start overwriting other things in memory. With that bug, we can totally reach the return address, the address on the stack that is executed after the ret call to return execution back to whatever code called it. For what to call, we see that the easy function will print the flag for us. Okay, very terse explanation of why overwriting the return address is the way to exploit that vulnerability. And then after the second one, they give you the explanation, which goes into detail about where, this way when the function is done executing and returns, code execution can pick up where it left off and the code knows where the stack is. These values make up the saved base pointer and saved return address, and in x86, the saved base pointer is stored at RBP plus 0, and the saved instruction pointer is stored at RBP plus 8. So when the ret instruction, the saved instruction pointer stored at RBP plus 8 is executed, this address is on the stack and we can reach, they go into a, it's not like a crazy involved explanation for sure, but it is a more complete explanation and more detailed around what is actually on the stack in the second challenge. So I don't know if they're just expecting you, if you didn't know this stuff already, to follow their walkthrough and just sort of go along with it, being unsure of what's happening, and then go through the next one, and then you'll get an explanation of what's happening. But we see the same structure here where pilot with the shellcode has no real explanation of what shellcode is. No explanation of what the shellcode itself is doing, let alone what the concept of shell, or it doesn't explain what the concept of shellcode really is, and it doesn't go into the details of the shellcode that is used. It's just, well, here's the shellcode. We got it from this other website where somebody did a write-up of this challenge, but, well, let's back up. But the point is, they also don't really explain it in their write-up. That's a very terse kind of write-up. They give an explanation of what the stack will look like, and what their steps are, but it's not really a walkthrough or explanation of how shellcode works and how to do this kind of exploit, which is fine. That's not necessarily what a write-up is for. You could just write up, here are the things that I did, and if people know their stuff already, this would be a useful explanation in case they weren't able to get that one. But here, in what is, in theory, a learning tool, they start off with no explanation of what a shellcode is or why you would use it. And then only in the next one do they go into some explanation of shellcode and how to find a shellcode and why we would inject it at a particular address, like why we would write it into memory so that we could then jump to it and execute it. And then they also have like a re-explanation of ASLR in case you didn't read the explanation from before. So, I don't know, this is just me kind of complaining about the structure, the pedagogical priorities, I guess, that are on display. Like, I feel like this would be, encouraging me to just follow through all of the write-ups without coming to an understanding of why, let alone getting to a point where I could develop the exploit myself and thus be it. Like, if you just go through these and do all the write-ups as laid out here and just follow the instructions in the write-ups, I don't think you're going to be in a position where, presented with one of these CTF challenges without a write-up, that you'd be able to actually develop the exploit and solve that challenge yourself. Which I don't like. That's not the learning outcome that I think they want for people going through these. Presumably they want people to then have experience to do the challenges themselves and be able to like find the exploit, whatever, or find the vulnerability, whatever it is, and then develop the exploit to get the flag. So they really should be putting these explanations before the challenges and then using the challenge itself as a way to show how that exploit, or like use the challenge as an example of the explanation you've already given rather than follow these steps without knowing what you're doing and then I will follow up with a very small explanation. That being said, it's way more work to write up that level of tutorial around what these concepts are and stuff. So I'm not, this is not me saying like, oh, they needed to do a better job. Like, they've already done a service to me for certainly by collecting all these things, but it may not be a sufficient learning tool for people that don't know the techniques already. I'm thinking back to when I had never done any buffer overflow exploits and whether I would be able to get through any of these without just following the steps in the walkthrough and then being like, well, I know that if I typed in the things that they told me to type in, it worked, which wouldn't leave me at a good position to feel confident to do it on my own. Okay, so they explain ASLR a little bit here, and yeah, they leak the address for us so that we can know what the return address should be overwritten to. And they use GDB to figure out the amount of space that they have. It's all good. Probably can also find that in Ghidra. Certainly Radar told me that. Or, I mean, it sort of just told me that because it's all references to that, and then I added the 4 bytes on it. Okay. And same kind of deal as the previous one. It's just we did this, we popped in the shellcode from this website, and we're off to the races. Sure. Perfectly fine. I'm always in favor of being able to understand what the shellcode is doing, but of course, I mean, assembly is not the easiest language to understand. The context that you need to be able to understand this stuff in the first place is quite a bit. It's almost like don't bother trying to understand assembly if you don't understand C kind of thing. And further beyond that, shellcode tends to be some very tightly crafted assembly code that, you know, looking at that 24-byte version of the 64-bit exec sh shellcode, like, you know, they were taking advantage of a lot of things about how of the different changes that a single instruction might make in order to minimize the number of instructions needed as much as possible, which is not necessarily the simplest thing, even if you understand the basics of assembly. You might see it in a binary because the compiler, you know, if you tell it minimize code size, the people writing the compiler know all those tricks, and so the compiler will end up using all those tricks to do very, you know, very compact code, although it may have its own limits to what it's allowed to do just because of the, you know, following certain standards, whereas shellcode, really the limit is just does it work or not on your target. Standard, you know, if it doesn't meet a standard but it still works on your target, doesn't matter what the standard says. Okay, next one. Let's see if we can get through this. 32-bit again. All right, no ASLR, no stack canaries, nothing preventing execution on the stack, so we're in the best possible position, I guess. Let's run it, see what we get. Gives me an address just for fun. Oh, interesting. Okay, I guess I am wrong about PIE being required for ASLR. Maybe you can get the stack to be randomized because there shouldn't be any absolute references to where the stack is. in your binary anyways. Your code should not have absolute references to stack addresses. Just conceptually, that's probably a poor choice. But the binary is going to be loaded at the same place. Like, we'll run that in the background. Oops. Why does that? Well, whatever. I was gonna like look at the maps for it, but I don't particularly care. So, all right, yeah, stack is gonna be at a different place every time. So we will read that in, and that's all good. Let's see how much space we have to work with. Okay, so we're getting into 48x, and we have gets, so we've got more than 64 bytes, and we push 4 after that, so we should have 4C, and then our return pointer. Do we write other stuff to... Doesn't look like we write anything after the gets call. We don't write anything to the stack, so we don't have to worry about it overwriting our shell code anywhere. But we do need to write dead beef to a particular location, otherwise we're going to call exit, which is not going to trigger the shellcode because it's not going to do a return. So we need to write 48 bytes, then dead beef, then 4 bytes doesn't matter. Is that accurate? I think so. And then what do we have for H? What does that get used for? And that gets moved into EBX. Is EBX just spilled onto the stack? I guess so. I don't know that I'm understanding that, but I think I don't have to care about what's in the contents of this variable. So we write our shell code, we've got, and then we write some amount of padding. Then we write dead beef to this location. That's just 4 bytes. And then, yeah, and then we have a total of 8 bytes of additional padding and the return address. And once again, just to double check, yeah, we're loading the address of the, so it's just printing us directly the start of the buffer that we're writing to. Okay. So I'm going to copy the exploit here, since we are retaining 32-bit for this. This one's going to be shell easy, have a, and then we'll receive the rest of that line. I'm not even going to put in the NOP sled. Okay, so we need padding for that amount. Um, 32-bit of dead beef, and then just keep with the hex. 8 bytes of additional padding, and then the return address. Nope. Okay. So, what have I done wrong? Do we end up with a new line character somewhere, maybe? Need to. No, we call send line. Okay. Well, let's run it in GDB. That would have been really nice if I managed to sort of one-shot that, but it's pretty unrealistic expectations for myself at this point. So we are not overriding the address at all. Let's run it again. Oh, well, first off, let's get the fixed address from GDB. And put that in the payload that we write out. And it's not getting dead beef at that address either. Okay, so okay, EBP is D4D0. No, 518. Let's see if there's some good commands to just print out more of the stack. Additional commands. Okay, we just want to add more commands, I guess. Context. Show me. That's cute. Or not cute, but that is useful. But what I really want is to show a larger amount of the stack. How do I get it to? Oh, it's pronounced Jeff. Okay. Might want to watch this video at some point, but alright, I will just live with. Let's look at. Just a word for. Oh, yeah, okay. I just forget they just use completely different terms than what x86 is used to. So look at that address, I guess. Let's look at a single word at D518, which is where EBP looks. Okay, so we are 8 bytes too far. Oh. Was the issue right? So we needed 40, not 48. Okay. Because the difference between there and where dead beef goes is 40. No, but we do get a sig fault, so that's good. Now we are actually getting to valid, like, overflow. Or, I mean, the overflow is happening, but we're actually controlling the return pointer. So that breakpoint on at the end. And what is ESP pointing to? It's not far enough. Maybe I would have thought 4 plus another 4 for the pushed. Well, let's take off 4. No. Okay. Alright, so now stack pointer points at this address, so go here. We are now we're not overriding the stack pointer. What has happened? Okay. Oh, I guess we need another 4. That's the issue. No, this looks like it is, right? Okay. And are we... Do we need to subtract even more from the stack pointer? Where is stack pointer at? D4, D8. Okay. Interesting. Okay. So right now, stack pointer is D5, 1C. We're at D4, D0. D5, 20. So now it's at D4, 80. Meaning we're probably still hitting into it. No, that tries to execute. Okay. Maybe that was enough. Yeah. Okay. So we just needed to, again, get the stack pointer out of the way of our shellcode. I wonder if there's a better way to handle that. So it's not just like a thing to do, when I notice in GDB that I am overwriting my shellcode with some of the pushes from it. Obviously, it would be less of an issue if your shellcode has fewer pushes. I don't think you can really avoid that entirely when you are doing the exec syscall, because it needs pointers to strings. You can't give a pointer to a register, so you need to put something in memory, and the stack is really the place that you have. But I mean, I don't see it mentioned in any of the shellcode that we've seen so far, I think. So their shellcode that they're using has been able to avoid it. Maybe it's just the nature of having a larger amount of shellcode from the Pontool Shellcraft. I don't know. I feel like it's something that I've encountered several times, even before the challenges in this course. But I haven't seen much explaining the need to do that. I've not seen, any tutorials that mention it. It starts to become kind of obvious once you see, like, well, now why does GDB say these instructions are different? Oh, it's because I just wrote to them when I did that push. But I mean, it would be nice to see an explanation of, either bringing that up or somebody telling me why I'm doing something poorly to need to do that in the first place, I guess. All right, we'll do this walkthrough, then we'll maybe look at the explanation of NX, XN, DEP, and then I think I'll call it there. for the stream. So yeah, shell it easy. Let's take a look at the binary. They run a file on it, 32-bit, then they run the program, give their standard input, and print a stack address and a prompt. Yeah. We look at the main function. We set the buffer to fairly small for input and output. Have a 64-bit input character, like we set the kernel buffering rather. I guess that's what vbuff is. I don't know what the V stands for. They have a yeah, I don't know what the V is about. But right, they set the buffer size to pretty small, and then they print out the pointer to our stack buffer and call gets, exactly the same as the previous one, with the notable exception, which we'll see. I guess Ghidra wasn't very good at decompiling that code, but you can see that it does a check about dead beef. They'll get into the assembly in a second. There's a character array input which can hold 64 bytes, which it prints its address. After that, it runs the function gets with input as an argument, allowing us to do a buffer overflow attack and get the return address. With that, we can get code execution. Our plan is to just push shellcode onto the stack, and we know where it is thanks to the info leak. Then we will overwrite the return address to the pointer to point to the start of our shellcode. We'll use shellcode that pops a shell for us when we run it. The shellcode I will use is from Shellstorm. It's the same one from the previous challenge, I guess. Also, there's a slight problem with our plan. That is, according to the decompiled code, the function exit is called. When this function is called, the ret instruction will not run in the context of this function, so we won't get our code execution. That is also true. However, the decompiled code isn't entirely correct. Looking at the assembly code gives us the full picture. It does have dead beef comparison, so we can see that there's a check to see if local C is equal to 0x dead beef, and if it is, the function does not call exit 0, and we get our code execution. When we look at the stack layout in Ghidra, we can see that this variable is within our means to overwrite, and it is at an offset of 0x40 relative to the beginning of our character buffer. Yep. So we just need to overwrite it with 0x deadbeef, and we will be good to go. Next, let's find the offset between the start of our input and the return address in GDB. They go through the same process that they always do, and they get 0x4c. Yeah, that seems correct. With that, we have everything we need to make the exploit. What did I end up needing to do? We do have it at 8. It was just the change from 40 to from 48 to 40, I guess, because the later attempt to change that to the 8 to a 4 was unnecessary. I think I was just not running the thing correctly. Or were there other changes I ended up needing to make and I don't remember what they are? Oh, and of course the stack size. Yeah. Okay. So we have everything we need to make the exploit, and they throw their shellcode in. They do the padding for that length. They put deadbeef on there. They do 8 bytes of additional padding. Shellcode, address to the beginning of that buffer. Looks good to me. And then they run it and they get the shell. One more thing they wanted to show, the shellcode we push on the stack can be disassembled to assembly instructions. let's break right at the ret instruction, which executes our shellcode. I did this by editing the breakpoint in the exploit to that and then running it. Editing the breakpoint in the exploit. I guess I'm not sure. Oh, I see. They have that attached at the beginning. I mean, I could try that, but I'll have to figure out why GDB attach is not working how I'm expecting it to work. I mean, it's either I'm missing a thing or I'm expecting it to work differently than it does or is intended to work. But yeah, they can look at that shellcode. I mean, it's also printed at this website. The C, this chunk of C, also, you know, they have it listed in not actually a comment, but conceptually a comment. But you can confirm. It's always a good idea to, you know, see if what's actually being understood by the processor is what you think is the code that you're running. So cool. Yeah, I mean, you know, my concern with the order in which they are explaining things as they go through these, I still kind of stand by that, but I get their idea of like, let's introduce one additional piece per challenge. So now in this one, they're like, hey, let's actually consider what the shellcode is now that we've solved this one. And that's, you know, I think it's reasonable to not go into detail about what the shellcode assembly is doing. And they aren't really going into detail, they're just showing how you could look at the shellcode, which can be really helpful for when you are debugging these as you go through them. Like, if you don't know what your shellcode is intended to look like as assembly instructions, then when it is incorrect in some way, maybe instead of jumping to D0, you jump to D1, and then it's decoding the rest of the instructions offset by 1, so they're completely different instructions than you intended. If you don't know what your instructions are supposed to be, you won't be able to notice that in GDB and go, hey, why is it doing a multiply and then shift and all this other stuff rather than the XOR and the push and push and push that I expected. So at least this is, you know, adding another layer of useful tip. But I still would have liked to see more of a breakdown of what shellcode is about before the first one. I don't know. That's just like, I guess I'm backseat teaching here, and they've put in the time to build this. So the idea of going from one that doesn't explain anything to one that explains more, maybe that's the right way to go. All right, last thing before I turn off the stream. Oh, we got somebody else. Yeah, I'm not that interested in real viewers. I only like robot viewers. They're much nicer. They will, you know, come in and spam stuff, and I don't have to talk to them. So thanks for the tip, though. Okay. NX is short for non-executable stack, or no execute bit, or however you want to think about it. And what it means is that the stack region of memory is not executable. So if there's perfectly valid code there, you can't execute it due to its permissions. For more on this, let's take a look at the memory mappings for binary that was compiled without this mitigation. Here it is with NX enabled. Whatever. So yeah, you look at the stack entry, and it's got read-write, but no X. And then with NX disabled, you've got read-write and X, and in fact, you've got read-write and X on a few different parts of, in fact, each library, each module, whatever you want to call it, has been loaded with one segment that is RWX, as well as some just not attached to any, not backed by any file kind of mapping, memory maps that have been set with RWX. So in theory, all of these are places that you could write instructions to and jump to if you knew the addresses, the start addresses for those maps, or just more generally, if there was data being written there by the program naturally. When we get to ROP stuff, you could use those for ROP gadgets. Anything with a execute bit on it is a valid place to look for ROP gadgets, is my understanding. I've actually never done a ROP exploit, but I'm looking forward to getting that practice when we get down to there. But as far as I understand it, you don't have to limit yourself to, the text segments or places that have natural instructions. If somebody writes data which happens to also be interpretable as instruction code, that is a gadget that you want, as long as that segment of memory is executable, then you're good to go. So we can see that for when NX is enabled, the stack has the memory permissions RW. When NX hasn't been enabled, the stack has memory permissions for RWX. So when NX is enabled, we can read and write to it. However, when NX isn't enabled, we can read, write, and execute code. Let's see what happens when we try to jump to somewhere in the stack, essentially executing data in the stack as code. Yes. While NX is enabled, and we get a seg fault. That's, you have a segment violation because the segment of memory does not have the permissions that you are trying to use for accessing it. We see here that as soon as we tried to execute code in the stack with NX enabled, we got a segv, sigsev, sure. This is because we tried to execute memory that was not executable. So what's the bypass? The typical bypass is to not execute code from the stack. If the memory permissions say you can't execute the code, you can't execute anything in that segment, then the way to handle that mitigation is actually just you don't handle that mitigation. You simply aren't able to do that. Maybe you could do a ROP chain that called whatever the memory map function stuff is to set the permissions to give you an executable stack or other segments executable. But if you can get a ROP chain that does that, you could probably get a ROP chain to do any other thing that you wanted anyways, and just have it run your syscall, and then you're good. Looking at the memory regions with NX enabled, we see that the PIE and libc memory regions have some executable memory space. Memory spaces where instructions are stored. We can leverage those to actually execute code through things like ROP, even though in a lot of instances we can't write to those memory regions since the memory permissions are RX. What is the PIE that they're talking about? Do they just mean... I don't know what the PIE memory region is. Maybe the name of the binary they're talking about is PIE. Yeah. Okay, so NX is just the way to, if you have that mitigation turned on, then the shellcode exploits that we were just doing will not work. And there's not really much to do about that. So, okay. Next time I stream, I will be going with this Boston Key Party 2016 Simple Calc challenge. As always, thank you for watching the stream or watching the video on demand recording. If you like what I have presented here, feel free to reach out to me on Twitter. Hamlet Online is my Twitter handle. It's my face right there. Or you go to hamlet.dev, which will redirect you to my GitHub page. And you can get my email address from there and look at the terrible code that I have not been writing a lot of these days. I need to get back on that. But yeah, that's all that I have. Thank you for watching if you're watching. This has been my longest stream so far by quite a bit, and my first stream, I think, where there were people in chat talking about stuff. So that was exciting for the little bit where I had some interaction with another person. Okay, I'm gonna switch back over to OBS. Chances are pretty good that since I haven't looked at OBS in a while, I've been on the Stream Manager in Twitch, OBS is just going to crash when I switch over to its window. If that's the case, I'll pop back in for a second to shut down the stream officially, but this is my extended, truly ending the stream goodbye.